The farthest human-made object ever built has been traveling at 38,000 miles per hour for almost 50 years. It has not yet covered 1% of the distance to a region most people have never heard of. Not another star, not another galaxy, a place still inside our own solar system. The Oort Cloud begins where everything familiar ends and stretches so far outward that crossing it would take longer than recorded civilization has existed. No probe we have ever launched will reach its far edge while still functioning. No signal we have ever sent will return from its depths in a single human lifetime. And the reason this matters is not what lives out there. It is what it reveals about how far we will never go. If this is the kind of deep science that keeps your mind running long after the video ends, a like and a subscribe genuinely helps us keep making these. We do not chase trends. We chase the questions that deserve your time. Now, are you comfortable? Let's begin. Close your eyes for a moment and picture the solar system. You already have an image. Everyone does. It was placed there when you were young, reinforced 1,000 times since, and it has never been seriously challenged by anything you have encountered in daily life. The picture looks something like this: a bright yellow star in the center, a series of planets arranged in neat, roughly circular orbits, spreading outward like rings on a target. Mercury is closest in, small and scorched. Venus is wrapped in acid clouds. Earth, blue and green and familiar. Mars, red and dusty, is increasingly present in the news. Then, the gas giants, Jupiter with its storm, Saturn with its rings. Uranus and Neptune are farther out, cold, pale, and largely ignored. And then, at the very edge, depending on when you went to school, Pluto. A tiny, frozen world sitting at the boundary of everything. The last stop before the void. That picture is not wrong. Every object in it is real. Every orbit is roughly where it should be. But the picture is catastrophically incomplete. And the way it is incomplete matters more than almost anything else in the story of what humans can and cannot do in space. Because the image in your head, the one with the planets and the sun and the neat orbital lines, represents less than 0.1% of the actual solar system. The real solar system is so much larger than that picture that comparing the two is like comparing a single parking space to the entire surface area of a continent. The objects you know, the planets you can name, the moons you have seen in photographs, all of them exist in a tiny, luminous huddle near the center of something so vast and so dark that most of it has never been visited, never been photographed, never been directly observed by any instrument ever built. And you have never been told this. Not clearly. Not in a way that changes how you think about what is possible out there. Let us fix that. Start with distances. In astronomy, there is a unit of measurement called the astronomical unit. 1 astronomical unit is the average distance from the Earth to the Sun, roughly 93 million miles. It is a useful yardstick because it makes the inner solar system easy to describe. Mercury orbits at about 0.4 astronomical units, Venus at about 0.7, Earth at 1, Mars at about 1.5. These are manageable numbers. They suggest a compact, navigable neighborhood. Move outward to the gas giants, and the numbers grow, but remain comprehensible. Jupiter orbits at roughly 5 astronomical units, Saturn at about 9.5, Uranus at about 19. Neptune, the outermost known major planet, orbits at approximately 30 astronomical units, 30 times the distance from the Earth to the Sun. That already sounds far, and in human terms, it is. It took the Voyager 2 spacecraft 12 years to reach Neptune after launching from Earth in 1977. 12 years of flight at speeds exceeding 35,000 miles per hour just to reach the last major planet. But here is where the picture you were given starts to fall apart. Neptune is not the edge of the solar system. It is not even close. Beyond Neptune lies the Kuiper Belt, a broad ring of icy objects, dwarf planets, and frozen debris that extends from roughly 30 astronomical units to about 50 astronomical units from the Sun. Pluto lives here. So does Eris, Marke, Haumea, and tens of thousands of other known objects, with likely hundreds of thousands more waiting to be found. The Kuiper Belt is where the New Horizons spacecraft went after its flyby of Pluto in 2015, continuing onward to visit the small Kuiper Belt object Arrokoth in 2019. As of 2026, New Horizons is still traveling outward at roughly 2.9 astronomical units per year and sits more than 60 astronomical units from the Sun. At that distance, the Sun is no longer the blazing disk that dominates Earth's sky. It is a small, intensely bright point of light, brilliant enough to distinguish from the surrounding stars, but no longer a presence you feel on your skin. You could block it with the tip of a pencil held at arm's length. The warmth is gone. The light is clinical, distant, the way a street lamp looks from the far end of a long road. And this is still the familiar part of the solar system. This is still close. Most people, if they think about the edge of the solar system at all, think of it as somewhere around here, the Kuiper Belt, the region past Neptune, the zone where Pluto and its icy cousins drift in cold silence. This is where the maps in textbooks tend to stop. This is where the mental picture fades to black. And this is precisely where the real solar system begins. Beyond the Kuiper Belt, there is a region so large that drawing it to scale on the same diagram as the planets is physically impossible without shrinking the inner solar system to a dot too small to see. This is the region where the Sun's gravitational influence still holds, still bends the trajectories of objects, still claims ownership of everything within reach. And that region does not end at 50 astronomical units, or 100, or even 1,000. It extends outward to roughly 100,000 astronomical units, perhaps 200,000. The estimates vary because no one has ever been there and no instrument has ever directly measured it. But the physics is clear. The Sun's gravity reaches far beyond anything the classroom map suggests. 100,000 astronomical units. Let that number register for a moment. Neptune orbits at 30. The Kuiper Belt fades somewhere around 50, and the Sun's gravitational domain stretches to 100,000. The familiar solar system, the one with the planets and the moons and the pretty rings, occupies a space that is less than 1/20th of 1% of the total volume the Sun controls. To picture this, imagine a football field. Place the Sun at one end and Neptune at the other. In that model, every planet in the solar system fits within the length of the field. Now ask where the edge of the Sun's gravitational influence falls on the same scale. The answer is roughly 3,300 football fields away, over 180 miles from the original field. Every planet, every moon, every ring, every asteroid you have ever heard of exists inside a single football field of space. The rest of the solar system, the overwhelming, crushing majority of it, stretches outward for 180 miles of dark, cold emptiness. That emptiness has a name. Most of it is called the Oort Cloud, and it is the subject of this story. But before we get there, we need to understand how we know the solar system is this large and what we have actually managed to send into that darkness. The answer to the second question is almost nothing. 5 spacecraft in the history of the human species have been launched on trajectories that will carry them out of the solar system. Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and New Horizons. Of these 5, only 3 are still communicating with Earth. Pioneer 10 sent its last detectable signal in 2003. Pioneer 11 went silent in 1995. The 3 survivors are the 2 Voyagers and New Horizons, and all 3 are running on borrowed time. Voyager 1 is the most distant. As of early 2026, It sits approximately 172 astronomical units from the Sun. It has been traveling since September 5, 1977, nearly 49 years of continuous flight. It moves at roughly 3.5 astronomical units per year, which translates to about 38,000 miles per hour. That is fast by any human standard. It is fast enough to cross the entire United States in less than 5 minutes. It is fast enough that no car, no train, no commercial aircraft could come close to matching it. And it has covered less than 0.2% of the distance to the outer edge of the Oort Cloud. Read that again. The fastest, most distant human-made object in existence, after nearly half a century of non-stop travel at 38,000 miles per hour, has not yet crossed 1% of the distance to the outermost boundary of our own solar system. It has not reached 1%. It is closer to the starting line than it is to anything resembling a finish. In November of 2026, Voyager 1 will reach a milestone that sounds impressive until you understand the scale it sits inside. It will become the first human-made object to travel one full light day from Earth. A light day is the distance light covers in 24 hours, approximately 16 billion miles. At that point, a radio signal sent from Earth to Voyager 1 will take 24 hours to arrive. A response will take another 24 hours to return. A simple exchange of information will consume 2 full days. And the Oort Cloud's inner edge is still at least 500 years of travel ahead of Voyager at its current speed. Its outer edge is roughly 30,000 years ahead. This is not a metaphor. These are calculated transit times based on measured velocity and confirmed distance estimates. 300 years to the inner boundary, 30,000 years to the far side. And Voyager will not be awake for any of it. Its radioisotope thermoelectric generators, which convert heat from decaying plutonium-238 into electrical power, are losing roughly 4 watts per year. As of 2026, only 2 scientific instruments remain operational. NASA engineers expect the spacecraft to lose its ability to return any data within the next several years. Sometime in the early 2030s, almost certainly before 2036, Voyager 1 will go silent. It will continue moving. Inertia does not care about power supplies. The spacecraft will drift outward through the darkness for millions of years, a small metal object cooling to the temperature of interstellar space, carrying a golden record that no one will ever play. It will pass through the inner Oort Cloud without knowing it. It will drift through the outer Oort Cloud without recording a single measurement. It will eventually exit the Sun's gravitational influence and become a true interstellar wanderer, long dead, long cold, long forgotten by the species that built it. And it will have completed its journey through the solar system roughly 30,000 years from now. 30,000 years. That is the number. The time it takes an object traveling at 38,000 miles per hour to cross the full diameter of the Sun's domain. For context, 30,000 years ago, modern humans were painting on cave walls in southern Europe. The last ice age had not yet reached its peak. Agriculture would not be invented for another 20,000 years. The entire span of recorded human history, from the first Sumerian tablets to the device you are watching this on, fits inside about 5,000 years. Voyager's crossing of the solar system will take 6 times longer than all of recorded civilization. And this is the fast route. This is the best we have ever done. The second Voyager, Voyager 2, is farther from the Sun than any other functioning spacecraft except its twin. It sits at approximately 142 astronomical units and moves at about 3.1 astronomical units per year, slightly slower than Voyager 1, because its trajectory after the Neptune flyby in 1989 carried it downward and out of the planetary plane at a different angle. It crossed the heliopause and entered interstellar space in November of 2018, 6 years after Voyager 1 did the same. Its power situation is similar. Its instruments are shutting down. Its voice is fading. New Horizons, the most recently launched of the 5, is the smallest and was the fastest at launch, but it has slowed to about 2.9 astronomical units per year and sits roughly 60 astronomical units from the Sun. It will never catch the Voyagers. It will not reach interstellar space as quickly, and its power supply will fail even sooner. These 3 spacecraft are the sum total of everything humanity has managed to push into the outermost reaches of the solar system. 3 small machines, all built in the 20th century, all dying, all moving at speeds that are laughable compared to the distances they still need to cover. Now here is the detail that changes the frame entirely. When people talk about the boundary of the solar system, they often confuse 2 very different things: the heliopause and the gravitational edge. The heliopause is the boundary where the solar wind, the stream of charged particles flowing outward from the Sun, loses its battle against the pressure of the interstellar medium. It sits at roughly 100 to 120 astronomical units from the Sun, depending on direction and solar activity. Both Voyagers have crossed it. This is why NASA describes them as operating in interstellar space, and that description is technically accurate. They are immersed in interstellar plasma. The solar wind no longer reaches them. By the standard of particle physics and plasma environments, they have left the Sun's direct influence. But by the standard of gravity, they have not left anything. The Sun's gravitational pull does not stop at the heliopause. It does not stop at the Kuiper belt. It extends outward, weakening with the square of distance, but never reaching zero, until it is finally overcome by the gravitational pull of other stars. That transition happens somewhere around 100,000 to 200,000 astronomical units from the Sun, and the space between the heliopause and that outermost gravitational boundary is almost entirely occupied by the Oort cloud. This means something extraordinary that most people have never considered. Interstellar space, the space between stars, as defined by the plasma and particle environment, begins inside the solar system. The Voyagers are already in interstellar space by one definition, and still deep inside the solar system by another. They are simultaneously between the stars and still within the Sun's gravitational domain. The solar system, in its fullest sense, extends far beyond the point where the Sun's light and wind give way to the cold medium between stars. And the overwhelming majority of that extended solar system is a place no human has ever seen, no spacecraft has ever reached, and no scientific instrument has ever directly measured. This is the first thing that needs to settle into your understanding before the rest of this story can land properly. The solar system is not what you think it is. It is not a tidy arrangement of planets around a central star. It is a vast gravitational territory, most of which is dark, empty, and cold beyond human experience, stretching outward for distances that make the planetary region look like a bright campfire surrounded by 1,000 miles of frozen wilderness. And the question this story is really asking is not what is out there in that wilderness. Astronomers have a reasonable theoretical picture of what the Oort cloud contains: trillions of icy bodies, frozen remnants of the solar system's formation, ancient objects drifting in orbits so wide that a single trip around the Sun takes millions of years. The question is what happens when humans try to go there? What happens when the species that has spent its entire history within the warm glow of the campfire tries to walk out into the darkness, not to a neighboring campfire, not to another star, but simply to the far edge of its own territory? What breaks first? What fails? What runs out? What gives way? Because the answer to that question is not dramatic. It is not a single catastrophic obstacle. It is not an alien threat, or a physical wall, or a radiation barrier that fries everything in its path. The answer is quieter than that, and in many ways worse. The answer is distance. Not distance as an inconvenience, distance as a force. distance that compounds across every system a mission depends on, until every system fails, not from damage, but from irrelevance. Distance that turns communication into monologue, rescue into fiction, resupply into memory, and human life into a footnote measured against the indifferent arithmetic of light speed and orbital mechanics. The Oort Cloud represents something that belongs to a different category entirely. The point at which distance itself becomes a kind of wall. It may not be a wall in the way most people understand walls. There is no surface to touch, no barrier to impact, no gate to unlock, but it may function as a wall in a more fundamental sense. The combined pressure of distance, time, isolation, and human limitation makes outward expansion not just difficult, but structurally impractical. Not because any single obstacle is insurmountable, but because the obstacles converge, and at that distance, the combined weight of all of them exceeds anything a realistic mission can absorb. That is the argument this story will make. Not as speculation, not as science fiction, but as a careful, grounded examination of what the numbers actually say when you line them up honestly and refuse to look away. The solar system you thought you knew was a small, bright room. The real solar system is a mansion so large that the room you knew is a closet near the entrance, and the rest of the mansion is dark. What fills that darkness and why it matters is where we go next. In 1950, a Dutch astronomer named Jan Hendrik Oort sat down with a problem that had been quietly bothering planetary scientists for decades. The problem was comets, not all comets, a specific category of them. The ones that arrived from nowhere, swung past the sun in long sweeping arcs, and then vanished back into the outer dark on orbits so elongated that they would not return for millions of years. These were called long-period comets. Unlike short-period comets such as Halley's, which loop around the sun every 75 years or so and stay relatively close to the plane of the planets, long-period comets came from every direction. They arrived from above, below, behind, and ahead. Their orbits were not confined to the flat disk where the planets lived. They rained inward from all angles, as if something enormous and spherical was throwing them toward the sun from every conceivable orientation. Oort gathered the orbital data on a small sample of known long-period comets and analyzed their trajectories backward, calculating where they must have originated before gravitational encounters with the planets bent their paths. What he found was striking. A large number of these comets had aphelia, the farthest point of their orbits, clustered around 20,000 astronomical units from the sun, not scattered randomly across a wide range, concentrated. As if there was a specific reservoir sitting at that distance, a vast collection of icy objects loosely held by the sun's gravity, occasionally disturbed by passing stars or galactic forces and sent tumbling inward on orbits that would carry them briefly through the warm planetary region before flinging them back outward again. Oort proposed that this reservoir existed, a spherical cloud of frozen bodies surrounding the entire solar system at enormous distance, containing billions or trillions of objects too small and too far away to see directly, but whose existence could be inferred from the comets they sent inward. The idea was not entirely original. An Estonian astronomer named Ernst Öpik had published a similar concept in 1932, but his work was largely ignored. Oort's analysis was more rigorous, more widely read, and better timed. The structure took his name. It has been called the Oort Cloud ever since. And in the 76 years since Oort published his paper, not a single object in the Oort Cloud has ever been directly observed. That sentence needs to sit with you for a moment because it defines everything that follows. The Oort Cloud is one of the most important structural features of the solar system. It is cited in every serious discussion of cometary origins, solar system boundaries, and interstellar transition zones. It appears in every textbook on planetary science. It is treated by the scientific community as an established component of the Sun's domain. And no human being, no telescope, no spacecraft, no sensor of any kind has ever directly detected a single object within it. The reason is not mysterious, it is mathematical. Objects in the Oort cloud are small, typically a few miles across at most, composed primarily of water ice, ammonia ice, and methane ice mixed with rock and dust. They are dark. They reflect almost no sunlight because the sunlight at those distances is negligibly faint, and they are staggeringly far away. Consider a reasonably large Oort cloud object, perhaps 12 miles in diameter, sitting at 2,000 astronomical units from the Sun, near the inner boundary of the cloud. At that distance, the object would have an apparent magnitude of roughly 42. That is more than 600,000 times fainter than the faintest objects detectable by the most powerful ground-based telescopes on Earth. Even the James Webb Space Telescope, the most sensitive infrared observatory ever placed in space, cannot see objects that dim at those distances. The Oort cloud is invisible, not because it might not exist, but because the laws of optics and the inverse square law of light make its individual members undetectable with any instrument currently available. So how do scientists know it is there? The answer is the comets. Every long-period comet that arrives in the inner solar system carries information about where it came from, encoded in its orbit. By running the orbital mechanics backward, astronomers can determine the farthest point the comet reached before it began its inward fall. When this analysis is done across hundreds of observed long-period comets, the pattern Oort, first identified in 1950, holds up. A large fraction of them originate from distances between roughly 20,000 and 50,000 astronomical units. They arrive from random directions, consistent with a spherical source rather than a flat disk. And their orbits suggest they were disturbed by some external force, either a passing star or the tidal pull of the Milky Way's galactic disk, which nudged them out of stable distant orbits and sent them sunward. This indirect evidence is strong. It is consistent across decades of observation. Multiple independent research groups have reached the same conclusions using different comet samples and different analytical techniques. The scientific consensus is firm. The Oort cloud exists. Its inner boundary lies somewhere between 2,000 and 5,000 astronomical units. Its outer boundary extends to at least 50,000 astronomical units and possibly as far as 100,000 to 200,000 astronomical units, where the Sun's gravity finally becomes too weak to hold objects against the gravitational pull of nearby stars and the broader Milky Way. But the cloud is not a uniform structure. Current models describe it as having two distinct regions, each with different properties and different dynamics. The outer Oort cloud is the part Oort himself originally described. It is roughly spherical, meaning it envelops the solar system in all directions like a shell. It extends from approximately 20,000 astronomical units to the outermost gravitational boundary. Objects here are loosely bound to the Sun. Their orbits are so wide that a single revolution takes millions of years. They move slowly, separated from one another by tens of millions of miles on average. The density is extraordinarily low. If you were somehow placed inside the outer Oort cloud, you would see nothing. The nearest icy body might be farther from you than the Earth is from the Sun. The Sun itself would be reduced to a bright star, perhaps the brightest star in the sky, but no longer recognizably different from the thousands of other stars surrounding it. This outer region is the most vulnerable to outside influence. Passing stars, even at distances of several light-years, exert enough gravitational pull to dislodge objects from their fragile orbits. The tidal force of the Milky Way's disk operates continuously, gently reshaping the cloud over millions of years. Objects on the outer fringe can be stripped away entirely, lost to interstellar space, no longer bound to the Sun at all. Astronomers estimate that the Oort Cloud has been slowly eroding since the solar system formed, losing members to passing stars and galactic tides across 4.5 billion years. The inner Oort Cloud, sometimes called the Hills Cloud, after astronomer Jack Hills, who proposed its existence in 1981, is a denser and more structured region. Rather than being spherical, it is believed to be shaped like a thick torus or donut, concentrated near the plane of the solar system's ecliptic. It extends from roughly 2,000 to 20,000 astronomical units. Because its volume is smaller than the outer cloud but may contain a comparable number of objects, the density of icy bodies in this region is significantly higher. Some estimates suggest that the inner cloud contains the majority of the Oort Cloud's total population, with the outer cloud being more diffuse and more sparsely populated. A paper published in 2025 proposed that the inner Oort Cloud might not be a smooth donut at all, but could have a spiral structure, shaped by the gravitational history of the solar system's interaction with passing stars and the galactic environment. If confirmed, this would add another layer of complexity to an already difficult picture. The internal geometry of the cloud may be more dynamic and less uniform than the simple models suggest. The total population of the Oort Cloud is estimated at somewhere between several hundred billion and several trillion individual objects. The total mass is harder to pin down. Estimates range from roughly 10 to 100 times the mass of Earth, depending on assumptions about the size, distribution, and composition of the objects. The most commonly cited figure is somewhere around 40 Earth masses, though this carries significant uncertainty. These are staggering numbers: trillions of objects, tens of Earth, masses of frozen material, distributed across a volume of space so immense that the planetary region of the solar system is a grain of sand by comparison. And yet the average density of the cloud is so low that it is virtually a vacuum. The objects are separated by such enormous distances that collisions between them are vanishingly rare. The cloud is simultaneously the largest structure associated with the Sun and one of the emptiest volumes of space imaginable. And it is entirely dark. No sunlight reaches its outer regions in any meaningful concentration. The Sun, from the perspective of an object at 50,000 astronomical units, would appear as just another bright star, several times brighter than Sirius, but no longer the dominant furnace that governs life on Earth. There is no warmth. Surface temperatures on Oort Cloud objects hover just a few degrees above absolute zero, roughly -454 degrees Fahrenheit, colder than any natural environment humans have ever encountered, colder than the surface of Pluto, colder than the vacuum of space near Earth. These are objects frozen so deeply and for so long that the ices within them have never experienced a thaw since the solar system was born. This is why comets from the Oort Cloud are scientifically precious. When a long-period comet falls inward and passes near the Sun for the first time, the heat vaporizes surface ices that have been frozen and undisturbed for 4.5 billion years. The gas and dust released carry chemical signatures from the original solar nebula, the cloud of gas and dust from which the Sun and all the planets formed. Studying these comets is like reading a letter sealed at the moment of the solar system's birth and opened for the first time in front of a telescope. This is exactly what happened in the summer of 2025, when an object designated 3I, Atlas, was detected by the Asteroid Terrestrial Impact Last Alert System Survey Telescope in Chile. Within days of its discovery on July 1st, astronomers confirmed from its velocity and trajectory that it was not a solar system native. It was the third confirmed interstellar object ever detected, following the enigmatic Oumuamua in 2017 and the comet 2I, Borisov, in 2019. But 3I Atlas was different in ways that mattered enormously for understanding distant icy bodies like those believed to populate the Oort Cloud. The comet was ancient. Analysis suggested it was approximately 7 billion years old, meaning it formed roughly 3 billion years before our own solar system existed. It came from the Milky Way's thick disk, a region populated by stars from an earlier, more violent epoch of galactic history. It had been drifting through interstellar space since before the Sun was even a condensing knot of gas in a stellar nursery. And when NASA's Spherics Space Telescope turned its infrared instruments on the comet in December of 2025, during a period when the object was erupting vigorously after its close pass by the Sun, the data revealed a composition rich in water ice, carbon dioxide, organic molecules, soot, and rock dust. The usual building blocks of early solar system material, locked in ice for billions of years and released for the first time as the comet crossed into the inner solar system's warmth. 3I Atlas was not an Oort Cloud object. It came from far beyond our Sun's gravitational reach, from a star system that no longer exists, but it was composed of the same primordial materials that Oort Cloud bodies are believed to contain. It was the same kind of object, forged in the same kind of environment, preserved by the same billions of years of frozen isolation. Studying it was, in a very real sense, studying what the Oort Cloud is made of without being able to reach the cloud itself. And it underscored a painful irony. The only way we currently have to learn about the composition of distant icy bodies is to wait for them to come to us. Either as long-period comets dislodged from the Oort Cloud by passing stars, or as interstellar visitors flung from other systems entirely. We cannot go to the cloud and sample it. We cannot send a probe to an Oort Cloud object and analyze its surface. We are dependent on the random generosity of orbital mechanics, waiting for the universe to deliver frozen messages from a region we may never visit. The chemical information carried by these visitors is scientifically invaluable. It tells us about the conditions in the protoplanetary disk where the solar system formed. It reveals which volatile compounds were present, in what ratios, and how they were distributed across the early system. It provides clues about the boundary conditions for planet formation, atmospheric evolution, and potentially the delivery of water and organic molecules to the young Earth. Every long-period comet that falls inward from the Oort Cloud is a data point from a library we cannot access any other way. But the visits are rare, brief, and uncontrollable. We cannot choose which object arrives or when. We cannot redirect a comet for closer study. We get a few weeks or months of observation as it swings through the inner system, and then it is gone, receding back into the dark on an orbit that will not bring it close again for millions of years, if ever. Now, one of the most important things to understand about the Oort Cloud is its relationship to the rest of the solar system's architecture. The cloud did not form where it currently sits. The icy bodies that populate it originated much closer to the Sun, in the region where the giant planets were forming. During the early history of the solar system, roughly 4 billion years ago, the gravitational interactions between the forming giant planets, particularly Jupiter and Saturn, were violent and chaotic. Vast numbers of small icy bodies were flung outward by close gravitational encounters with these massive worlds. Some were ejected from the solar system entirely. Others were thrown into extremely wide orbits that carried them thousands or tens of thousands of astronomical units from the Sun. Over time, the gravitational influence of passing stars and the galactic tide reshaped these orbits, randomizing their orientations and pulling them into the roughly spherical distribution we infer today. The Oort Cloud is, in a real sense, the solar system's graveyard of failed planets. Icy bodies that might have become part of a planet or a moon were instead exiled to the outermost darkness by the gravitational politics of the inner solar system's formation. They have been drifting there ever since, unchanged, untouched, unseen. The mechanism that built the Oort Cloud is one of the most violent chapters in the solar system's history, and understanding it reveals why the cloud exists in the form it does. For the first several 100 million years after the Sun ignited, the solar system was a fundamentally different place. The giant planets were not in their current orbits. Jupiter and Saturn were closer together and closer to the Sun. Uranus and Neptune were closer in as well, and their positions relative to each other may have been reversed from what we see today. The region beyond the giant planets was densely populated with small, icy bodies, a massive disk of primordial material left over from the formation process, containing perhaps 35 to 50 Earth masses of frozen debris. Then something changed. Gravitational interactions between Jupiter and Saturn shifted their orbital resonance. Saturn moved outward. This destabilized Uranus and Neptune, which were pushed into the dense outer disk of icy bodies. The encounters were catastrophic. Neptune plowed through the disk like a ship through a harbor full of small boats, scattering trillions of icy bodies in every direction. Some were flung inward, briefly crossing the orbits of the inner planets. Some were ejected entirely from the solar system, sent flying into interstellar space, never to return. And a significant population was thrown outward into extremely wide orbits, carrying them thousands and tens of thousands of astronomical units from the Sun, where the gravitational influence of passing stars and the tidal pull of the galactic disk gradually reshaped their trajectories into the roughly spherical distribution we infer today. This model, known broadly as the Nice model after the French city where it was first developed, has undergone significant refinement since its original publication in 2005. Variations have been proposed that adjust the timing, the sequence of planetary movements, and the specifics of how the disk was disrupted. But the core picture remains robust. The Oort Cloud was not built gently. It was built by the most violent gravitational upheaval the solar system has ever experienced. It is a fossil record of planetary chaos, a permanent archive of the moment when the giant planets rearranged themselves and threw half the solar system's small body population into the abyss. This origin also explains why the cloud is so distant and so diffuse. The icy bodies were not placed at 20,000 astronomical units by a gradual process. They were hurled there by close gravitational encounters with planets millions of times their mass. The energy imparted to them was enormous. Their resulting orbits were wildly elongated, stretching from a few hundred astronomical units at closest approach to tens of thousands at their farthest. Over billions of years, the gentle reshaping forces of passing stars and galactic tides circularized some of these orbits and randomized their orientations, building the spherical shell that Oort first inferred from comet trajectories. But the raw material was supplied in a burst of violence that lasted perhaps a few 100 million years and then stopped. The Oort cloud is not replenished. It is slowly consumed. Every comet dislodged from the cloud and sent inward is one fewer member. Every object stripped away by a passing star is lost permanently. The cloud that exists today is smaller than the cloud that existed 2 billion years ago, and the cloud that will exist 2 billion years from now will be smaller still. It is a finite, diminishing reservoir, a remnant of a catastrophe that happened once and will not happen again. There is a small number of observed objects that may represent the innermost fringe of the cloud or the transitional zone between the Kuiper belt and the inner Oort cloud. The most famous of these is Sedna, discovered in 2004. Sedna follows an extraordinarily elongated orbit that carries it from a closest approach of 76 astronomical units from the Sun out to roughly 937 astronomical units at its farthest point. Its orbital period is approximately 11,400 years. It is too distant to be a typical Kuiper belt object and too close to be a classical Oort cloud member. It sits in a transitional zone that some astronomers call the Sednoid region, a handful of objects with extreme orbits that may represent the scattered inner boundary of the Hills cloud. Another candidate is 2012 VP 113, discovered in 2012, with a perihelion of about 80 astronomical units and an aphelion somewhat smaller than Sedna's. Other candidates include 2010 GB, 174, and the object designated 474640 Alicanto. Together, these objects form a sparse but tantalizing hint that the inner Oort cloud has a real population of large bodies waiting to be found if telescopes ever become sensitive enough to see them. But even these candidates are at the near edge of the near edge. The main body of the Oort cloud, the trillions of objects drifting between 10,000 and 100,000 astronomical units, remains entirely beyond the reach of direct observation. And unless there is a dramatic leap in telescope technology or a spacecraft mission lasting centuries, it is likely to stay that way for a very long time. Now here is where the Oort cloud's position in the larger architecture of the solar system becomes critical to this story. The heliopause, where the solar wind gives way to the interstellar medium, sits at roughly 100 to 120 astronomical units. Both Voyager spacecraft have crossed this boundary. They are immersed in interstellar plasma. They are, by the standards of particle physics, in interstellar space. But the Sun's gravitational influence does not end at the heliopause. It continues outward, weakening steadily, until it is finally overwhelmed by the combined gravitational pull of other nearby stars and the broader galactic mass. This gravitational boundary, sometimes called the Hill sphere of the Sun, lies at roughly 100,000 to 200,000 astronomical units. The Oort cloud fills the space between the heliosphere and this gravitational edge. This creates a remarkable and deeply counterintuitive situation. Most of the solar system, measured by volume, is interstellar in its environment, but solar in its gravity. The space occupied by the Oort cloud is filled with interstellar plasma. It is exposed to galactic cosmic rays. It is bathed in the diffuse radiation of the Milky Way rather than the light of the Sun. By every measure of the local physical environment, it is the space between stars. And yet the objects drifting through this space are gravitationally bound to the Sun. They orbit it, they belong to it. They are part of its system in the deepest mechanical sense. The solar system, in its fullest definition, is an object that extends into interstellar space. It is not contained by the heliosphere. It overflows it by a factor of roughly 1,000. The warm, sheltered, radiation-shielded bubble of solar wind that protects the planets is a tiny pocket at the center of a gravitational domain that reaches far into the cold, unshielded medium between the stars. And this has consequences. Real, practical, mission-relevant consequences that most discussions of space exploration never address. Because when people talk about humanity leaving the solar system, they almost always mean leaving the planetary region, passing Neptune, clearing the Kuiper belt, maybe crossing the heliopause the way the Voyagers did. That feels like leaving. It sounds like leaving. The press releases say leaving. But the Oort cloud is still out there, thousands and thousands of astronomical units of gravitational territory that the Sun still claims. And crossing it is a challenge so fundamentally different from anything humans have attempted that the comparison barely holds. Consider the difference in what the heliosphere provides versus what the Oort cloud removes. Inside the heliosphere, the solar wind creates a magnetic bubble that deflects a significant portion of galactic cosmic radiation. It is not a perfect shield, but it measurably reduces the radiation flux experienced by spacecraft and any humans aboard them. Outside the heliosphere, in the interstellar medium where the Oort cloud sits, that shield is gone. Cosmic ray exposure increases. The energetic particle environment becomes harsher. Any spacecraft traveling through this region would need its own radiation shielding, adding mass, adding cost, adding complexity to a mission that is already straining against every engineering limit. The radiation problem deserves considerably more attention than it typically receives in discussions of deep space exploration, because it is not a hazard that can be engineered away with moderate effort. It is a fundamental constraint imposed by the particle environment of interstellar space, and it becomes dramatically worse once a spacecraft leaves the protective bubble of the heliosphere. Inside the heliosphere, the solar wind creates a magnetic barrier that deflects a substantial portion of incoming galactic cosmic rays. These are not the relatively low-energy particles shed by the Sun during solar flares. Galactic cosmic rays are atomic nuclei, predominantly protons but including heavier ions up to iron, accelerated to near-light speeds by supernova shock waves, active galactic nuclei, and other extreme astrophysical processes. They carry enormous kinetic energy. In the most extreme case ever recorded, a single cosmic ray particle carried the kinetic energy of a baseball lobbed at 60 miles per hour, compressed into a single atomic nucleus. Most galactic cosmic rays carry far less energy individually, but their cumulative biological effect over years of continuous exposure is what makes them dangerous. When these particles strike solid matter, they do not simply bounce off. They penetrate deeply, smashing through atomic structures and generating cascades of secondary particles that spread damage far beyond the initial impact point. Inside the heliosphere, the flux of galactic cosmic rays is measurably reduced. The solar magnetic field and the outward pressure of the solar wind act as a partial shield, turning away or decelerating lower-energy cosmic rays before they reach the inner solar system. This shielding fluctuates with the solar cycle. During solar maximum, when the Sun's magnetic field is strongest and most turbulent, cosmic ray flux at Earth drops by roughly 15 to 25% compared to solar minimum. Even so, cosmic rays remain a significant concern for astronaut health on the International Space Station and would be a major hazard on any mission to Mars. Outside the heliosphere, the shielding disappears. The Voyager spacecraft, after crossing the heliopause, measured a sharp increase in galactic cosmic ray intensity. The particle environment in interstellar space is harsher, more energetic, and more constant than anything inside the heliosphere, and the Oort Cloud sits entirely within this unshielded environment. Every mile of travel through the cloud is a mile traveled under the full bombardment of galactic cosmic radiation, without any natural protection. The biological consequences of prolonged exposure to galactic cosmic rays are severe and well documented in the research literature. Unlike the electromagnetic radiation from the Sun, which can be blocked by relatively thin layers of material, galactic cosmic rays are so energetic that they penetrate through meters of solid shielding. Conventional spacecraft hulls offer minimal protection. Even dedicated radiation shielding made from materials optimized for particle absorption, such as polyethylene or water, must be extremely thick to reduce the dose significantly. A study by NASA's Space Radiation Analysis Group found that achieving a meaningful reduction in cosmic ray exposure for a Mars-duration mission would require shielding masses measured in tens of thousands of kilograms. For a mission lasting decades or centuries through the full galactic cosmic ray environment, the mass requirements would be extraordinary. The biological damage from galactic cosmic rays is not limited to acute radiation sickness, which occurs only at very high doses. The primary concern for long-duration missions is the cumulative effect of chronic low-dose exposure on cellular DNA. Heavy cosmic ray ions, particularly iron nuclei, create dense tracts of ionization damage as they pass through biological tissue. These tracts are difficult for cellular repair mechanisms to fix correctly. The result, over years of exposure, is an increasing burden of unrepaired or incorrectly repaired DNA damage that elevates the risk of cancer, cardiovascular disease, and central nervous system degradation. NASA currently limits astronaut career radiation exposure to levels associated with no more than a 3% increase in lifetime cancer risk. A mission through the Oort Cloud, lasting decades under full galactic cosmic ray bombardment, would exceed this limit within the first few years unless shielding far beyond current capability were provided. And shielding creates its own problem. More shielding means more mass. More mass means more fuel to accelerate. More fuel means a larger spacecraft. A larger spacecraft means more structural material, more power demand, more thermal management complexity. The mass penalty of adequate radiation shielding cascades through every other system on the spacecraft, compounding costs and engineering difficulty at every stage. Consider communication. At 100 astronomical units, roughly where the Voyagers are now, a radio signal takes about 14 hours to reach Earth. That is already a severe operational constraint. NASA cannot have a real-time conversation with either Voyager. Commands are sent and responses are awaited across a gap of more than a full day. At 1,000 astronomical units, inside the inner edge of the Oort Cloud, the one-way light time is approximately 5.8 days. A round-trip message takes nearly 12 days. At 10,000 astronomical units, the middle of the inner cloud, a message to Earth and back takes roughly 115 days. Nearly 4 months of silence between asking a question and hearing the answer. At 50,000 astronomical units, in the outer cloud, the round-trip time is roughly 19 months. 19 months. A crew sending a distress signal from the outer Oort Cloud would wait a year and a half for a response. And even then, the response would be nothing more than words, traveling at the speed of light through a void so vast that the signal itself would have weakened to the point of near undetectability. The Deep Space Network, the system of massive radio antennas that currently communicates with the Voyagers, struggles to maintain contact at 170 astronomical units. At 50,000 astronomical units, the signal would be so faint that no existing receiver on Earth could extract it from the background noise without antenna arrays orders of magnitude larger than anything currently built or funded. Communication does not simply become delayed at Oort Cloud distances. It degrades beyond the threshold of operational usefulness. A mission operating in the outer cloud would be, for all practical purposes, alone. Not in the romantic sense of a ship at sea out of sight of shore. In the absolute sense of an object so isolated from its origin that no message, no instruction, no reassurance, and no rescue plan could reach it within a time frame that matters to the humans aboard. This is one of the dimensions that separates the Oort Cloud from every other region of the solar system. The Kuiper Belt is remote, the outer planets are far. But a spacecraft at 50 astronomical units can still receive instructions from Earth within hours and send data back on the same timeline. The link is strained but functional. The connection to home is thin but real. In the Oort Cloud, that connection dissolves. Not because it is physically severed. Light still travels, radio waves still propagate. But the delay grows so long and the signal so weak that the connection becomes a formality. You are technically still able to send a message. You are practically shouting into a canyon so deep that the echo returns after everyone who was listening has left. And communication is only one of the systems that breaks down at these distances. Power is another. Propulsion is another. Human endurance is another. Structural maintenance is another. Each of these will be examined in detail in what comes next. But the point here, the point that the structure and position of the Oort Cloud forces us to confront, is that this region of the solar system is not simply farther away. It is qualitatively different from anything closer. The inner solar system is a place where human technology works. The outer planetary region is a place where it strains. The Kuiper Belt is a place where it reaches its current limit. The Oort Cloud is a place where the assumptions underneath the technology begin to collapse, not because the physics changes. The laws of nature are the same at 50,000 astronomical units as they are at 1. But because the scale changes by so much and in so many dimensions simultaneously that every engineering margin, every safety factor, every redundancy that makes spaceflight survivable at shorter distances is exhausted before the mission is half begun. The Oort Cloud is not an obstacle. It is not a hazard. It is not a wall in any physical sense. It is a region of space defined by its emptiness, its darkness, its cold, and its staggering distance from everything humans have ever known. And that may be precisely what makes it the most formidable boundary the human species has ever faced. What it would actually take to send something there, and what would happen to anything we sent, is where this story goes next. Every spacecraft humanity has ever sent beyond Mars shares a single defining trait. It was designed to survive a journey measured in years, perhaps a decade or two at most, across distances measured in tens of astronomical units. The engineering, the power systems, the communication architecture, the thermal protection, all of it was built around a basic assumption. The mission would operate within a regime where Earth could still see the spacecraft, still talk to it, still send it instructions, and still receive its data within a time frame that allowed human beings on the ground to respond, adjust, and intervene. That assumption works at the scale of the planets. It strains at the scale of the Kuiper Belt, and it collapses entirely at the scale of the Oort Cloud. To understand why, you cannot examine the problems one at a time and then add them together. That is not how they work. The problems are multiplicative. Each one makes the others worse. Distance increases travel time. Travel time increases power demand. Power demand increases mass. Mass reduces speed. Reduced speed increases travel time further. Communication delay eliminates real-time guidance. Lack of guidance increases failure risk. Failure at extreme distance eliminates rescue. And the absence of rescue transforms every minor malfunction from a solvable inconvenience into a potential death sentence for the mission. This is the compounding effect that makes the Oort Cloud qualitatively different from any destination humanity has ever contemplated reaching. Not one unsolvable problem. A cascade of solvable problems that arrive simultaneously at a scale where none of the solutions work. Start with propulsion, because everything else flows from how fast you can go and how long it takes to get there. The fastest spacecraft ever launched relative to the Sun was the Parker Solar Probe, which reached speeds exceeding 430,000 miles per hour during its closest approaches to the Sun. But that speed was achieved through gravitational acceleration during solar flybys and is not sustained during outbound travel. The spacecraft is not heading outward, it is diving inward. Its velocity at the bottom of its orbit has no relevance to the problem of reaching the outer solar system. For outbound missions, the numbers are different. Voyager 1, the fastest object currently leaving the solar system, moves at roughly 38,000 miles per hour relative to the Sun. New Horizons launched faster than any spacecraft before it, but has since slowed to roughly 30,000 miles per hour. The proposed NASA interstellar probe concept, currently in the study phase at the Johns Hopkins Applied Physics Laboratory, envisions a spacecraft that would use a close solar flyby combined with a Jupiter gravity assist to achieve speeds of 6 to 7 astronomical units per year, roughly double the Voyager rate. This would represent a genuine advance. At 7 astronomical units per year, the probe could reach 375 astronomical units in about 50 years, and potentially 1,000 astronomical units in its extended mission lifetime. That sounds promising until you apply it to the Oort Cloud. At 7 astronomical units per year, reaching the inner edge of the cloud at 2,000 astronomical units would take approximately 285 years. Reaching 20,000 astronomical units, the transition zone between the inner and outer cloud would take roughly 2,800 years. Reaching the outer boundary at 100,000 astronomical units would take over 14,000 years. The interstellar probe, if it is ever approved, funded, built, and launched, would represent the most ambitious deep space mission in human history. It would more than double the speed of any previous outbound spacecraft, and it would not reach the midpoint of the Oort Cloud within the lifespan of any civilization that has ever existed on Earth. What about more advanced propulsion? Nuclear thermal propulsion, nuclear electric propulsion, and solar sails have all been studied as ways to achieve higher speeds for deep space missions. Each offers improvements over chemical rockets, but none changes the fundamental arithmetic by the orders of magnitude required. Nuclear thermal rockets, which heat a propellant using a nuclear reactor, can achieve roughly twice the exhaust velocity of the best chemical engines. This translates to higher spacecraft speeds for a given amount of fuel, but the gains are incremental, not transformative. A nuclear thermal spacecraft might reach 8 or 10 astronomical units per year with an aggressive mission design. That still puts the inner Oort Cloud edge at 2 centuries of travel and the outer boundary at 10,000 years. Solar sails, which use the pressure of sunlight on a large reflective surface to accelerate without fuel, offer a different advantage. They carry no propellant, so they can accelerate continuously as long as they remain close enough to the sun for radiation pressure to be significant. A solar sail, performing a close flyby of the sun, swooping within a few solar radii to maximize the radiation push, could theoretically achieve speeds of 15 to 20 astronomical units per year. This is a meaningful improvement. At 20 astronomical units per year, the inner Oort Cloud edge arrives in a century, the outer boundary in 5,000 years. But solar sails face engineering challenges that have never been solved at mission scale. The sail must be enormous, potentially hundreds of meters across, and constructed from material thin enough to be pushed by photons, yet strong enough to survive the thermal and gravitational stresses of a close solar pass. No such sail has been built. The largest solar sail ever deployed in space, the Japanese Ikaros mission, measured roughly 14 meters across and demonstrated the concept at a very small scale. Scaling this to the size needed for an Oort Cloud mission represents an engineering challenge that is measured in decades of development, if it is feasible at all. There are more speculative propulsion concepts. Laser-driven light sails, in which a ground-based or space-based laser array pushes a small reflective spacecraft to a significant fraction of the speed of light, have been proposed under the Breakthrough Starshot initiative. This concept envisions gram-scale spacecraft accelerated to roughly 20% of light speed, fast enough to reach Alpha Centauri in about 20 years. At that speed, the entire Oort Cloud could be crossed in a matter of days. But Breakthrough Starshot is not an engineering program. It is a research initiative exploring the feasibility of the concept. The laser array required would need to deliver roughly 100 gigawatts of power to a sail roughly 4 meters across. For reference, 100 gigawatts is approximately the total electrical generating capacity of a mid-sized country. The sail material would need to survive being hit by that beam without vaporizing, a materials science problem that has not been solved. The spacecraft would be so small that it could carry no meaningful instruments by current standards. No camera, no spectrometer, no communication system capable of sending data back across interstellar distances. And the cost estimates for the full system range from $5 billion to $10 billion, for a technology that would produce flyby measurements lasting fractions of a second as the tiny sail screams through the target system at 60,000 kilometers per second. Even if every one of these challenges were overcome, and even if the system were scaled up to carry a meaningful scientific payload, it would be a robotic flyby mission. It would pass through the Oort Cloud in hours and keep going. It would not stop. It would not orbit. It would not linger. It would be a bullet, not a visitor. And it would tell us almost nothing about what the Oort Cloud is like as a place, because it would never stay long enough to find out. For a mission that actually reaches the Oort Cloud, enters it, studies it, and returns data over time, The speed must be high enough to arrive within a practical time frame, but low enough to allow the spacecraft to operate in the region rather than passing through it. And no propulsion system that currently exists or is under serious development can deliver both of those requirements at Oort Cloud distances. Now, layer on the power problem. Every spacecraft that operates in deep space needs electrical power. In the inner solar system, solar panels work well. Sunlight is abundant. Panels can be sized to meet the spacecraft's needs with reasonable mass and cost. But solar power fades with the square of distance from the Sun. At Jupiter, 5 astronomical units out, sunlight is roughly 4% as intense as at Earth. Solar panels can still work there, but they must be much larger. The Juno spacecraft orbiting Jupiter carries 3 solar arrays, each nearly 30 feet long. At Saturn, 9.5 astronomical units out, solar intensity drops to about 1% of Earth's level. Beyond Saturn, solar power becomes impractical. Every deep space mission past Saturn has relied on radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium-238 into electricity. The Voyagers carry them. New Horizons carries one. The Cassini mission to Saturn carried 3. Radioisotope generators are reliable. They have no moving parts. They function in complete darkness, and they decay. Plutonium-238 has a half-life of roughly 87.7 years. The thermocouples that convert heat to electricity degrade independently of the fuel. Together, these effects cause the power output to drop by about 4 watts per year. Voyager 1 launched with roughly 470 watts of electrical power. It now produces somewhere around 220 watts. Within the next decade, it will no longer produce enough to run even a single scientific instrument. A mission to the inner Oort Cloud, even at the optimistic speed of 7 astronomical units per year, would need to operate for nearly 3 centuries. No radioisotope generator can function for 3 centuries. The plutonium itself would have passed through more than 3 half-lives, reducing its heat output to less than 15% of the starting value. The thermocouples would have degraded further. The total electrical power available after 300 years would be a tiny fraction of what was available at launch. There are alternative power concepts. Small nuclear fission reactors, which split uranium or other fissile material to generate heat, can produce more power and potentially last longer than radioisotope generators. NASA and the Department of Energy have tested fission power systems for space use, and the technology is further along than many people realize. A compact fission reactor could potentially provide kilowatts of power for decades, but decades is not centuries. And centuries is what the Oort Cloud requires. Even the most optimistic projections for space-rated fission systems describe operational lifetimes of 20 to 40 years. Extending that to 300 years would require either multiple redundant reactors, which adds enormous mass, or breakthroughs in reactor materials and fuel cycle management that do not currently exist. The engineering challenge is not building a reactor that works in space. It is building one that works in space for longer than any machine in human history has ever continuously operated. Now layer on the communication problem, which we touched on earlier, but need to examine here in its full operational weight. At Oort Cloud distances, communication with Earth is not just delayed, it is degraded. Radio signals weaken with the square of the distance. A signal that is perfectly readable at 100 astronomical units becomes 10,000 times weaker at 10,000 astronomical units. The Deep Space Network, NASA's array of large radio antennas in California, Spain, and Australia, is the most sensitive deep space communication system on Earth. It is currently operating near its limits to maintain contact with the Voyagers at roughly 170 astronomical units. The data rate from Voyager 1 has been reduced over the years to approximately 160 bits per second. For comparison, A typical home internet connection delivers data at millions of bits per second. At 1,000 astronomical units, maintaining even Voyager-level data rates would require either a transmitter on the spacecraft far more powerful than anything Voyager carries, or a receiving antenna on Earth far larger than anything in the deep space network. At 10,000 astronomical units, the requirements become extraordinary. At 50,000 astronomical units, they become, by any current engineering standard, impossible. Optical communication, using lasers instead of radio waves, offers higher data rates and tighter beam focus, which reduces signal spreading. NASA's Deep Space Optical Communications experiment, tested aboard the Psyche spacecraft in 2023 and 2024, demonstrated laser communication from distances beyond the Moon. The technology is promising for inner solar system missions. But at Oort Cloud distances, the same inverse square law applies. The laser beam spreads, the signal weakens, the receiving telescope on Earth must be enormous and exquisitely sensitive, and the pointing accuracy required on the spacecraft, maintaining a laser beam aimed at Earth from tens of thousands of astronomical units away while the spacecraft rotates and vibrates, demands a level of precision that scales beyond current technology. The practical consequence is this: a spacecraft in the Oort Cloud would be unable to send or receive data at any useful rate unless communication technology advances by orders of magnitude beyond what currently exists. And even then, the delays would render real-time interaction impossible. Instructions sent from Earth would arrive days, weeks, or months later. Data sent back would take equally long. The spacecraft would need to be fully autonomous, capable of making every decision about its own operation, its own science priorities, its own fault recovery, and its own survival, without any input from home. This is not merely an engineering requirement, it is a philosophical transformation in what a space mission means. Every mission in the history of human spaceflight has been, at its core, a partnership between the crew or spacecraft in space and the team on Earth. The ground has always been there, watching, advising, correcting, ready to intervene. That partnership is what makes spaceflight survivable. Astronauts aboard the International Space Station are in constant contact with mission control. Mars rovers receive daily command sequences from operators on Earth. Even the Voyagers, at the ragged edge of communication capability, still receive and execute commands from the Jet Propulsion Laboratory. In the Oort Cloud, that partnership ends, not because the will to maintain it is absent, because the physics forbids it. The speed of light is finite, the distances are too great, the signal is too weak. A spacecraft in the outer cloud is alone in a way that no human-built object has ever been alone. It is alone the way a bottle dropped in the deep ocean is alone, technically still part of the same planet, practically unreachable by any means. Now layer on the human factor. Because everything described so far assumes a robotic mission, the problems become categorically more severe if any human being is aboard. No human has ever spent more than approximately 437 consecutive days in space. That record was set by Valery Polyakov aboard the Mir space station in 1994 and 1995. The physiological effects of that duration included bone density loss, muscle atrophy, cardiovascular deconditioning, and changes in vision associated with increased intracranial pressure. All of these effects are manageable over a period of 1 to 2 years with exercise, medication, and the prospect of returning to Earth's gravity. A crewed mission to the inner Oort Cloud, even at speeds far beyond current capability, would last decades at minimum, more realistically, centuries. The human body does not function in microgravity for decades. Artificial gravity, produced by rotating the spacecraft, is a theoretical solution but adds enormous structural complexity and mass, Radiation shielding against galactic cosmic rays, which are unimpeded in the interstellar medium where the Oort cloud sits, requires either massive physical shielding or active electromagnetic deflection systems, neither of which has been demonstrated at the scale needed. The psychological effects of complete isolation from Earth, from any other human community, from any possibility of rescue or return, over periods measured in generations, are entirely unknown. No analog exists. No experiment has been run. No data is available. A crude Oort Cloud mission would not be a voyage. It would be a permanent exile. The crew who departed would not return. Their children might not return. Their grandchildren might not return. The mission would need to be self-sustaining in every dimension: food, water, air, medical care, manufacturing, education, governance, and social stability. Across centuries of travel through absolute darkness with no possibility of resupply, reinforcement, or communication with the civilization that launched them. This is not space exploration as any human institution has ever practiced it. This is the founding of a self-contained civilization inside a metal shell aimed at a destination that offers nothing upon arrival. No atmosphere, no resources, no surface to land on, no warmth, no light. Only scattered icy objects separated by millions of miles of vacuum at temperatures near absolute zero. And finally, layer on the one factor that ties all the others together: rescue. In low Earth orbit, a spacecraft in trouble can be reached within hours. The space shuttle was designed with abort modes that could return the crew to Earth in minutes. The International Space Station has Soyuz and Crew Dragon vehicles docked at all times, ready for emergency evacuation. Even a lunar mission offers the possibility of return within days. A Mars mission stretches this margin. In an emergency, a crew on Mars cannot return to Earth for months, possibly over a year, depending on orbital alignment. This is one of the most serious concerns in Mars mission planning. The gap between emergency and rescue is measured in months. It is a hard problem. It is a problem that mission designers take very seriously. In the Oort Cloud, the concept of rescue does not exist. Not practically, not theoretically, not in any meaningful sense. A crew at 10,000 astronomical units experiencing a critical systems failure would send a distress signal that takes 58 days to reach Earth. If Earth could somehow respond instantly, the response would take another 58 days to arrive. Nearly 4 months between the emergency and the first word of advice. And advice is all it could be. No rescue ship could be launched, accelerated, and delivered to the location within any human-relevant timeframe. The crew would be dead or saved by their own actions long before any response from Earth could matter. This is the dimension that transforms the Oort Cloud from a difficult destination into something more fundamental. It is not merely that the journey is long. It is not merely that the communication is slow. It is not merely that the power fades, or the radiation increases, or the human body weakens. It is that all of these things happen together, each reinforcing the others, and the cumulative effect is the total withdrawal of every form of support that has ever made human spaceflight survivable. In the inner solar system, a mission fails gracefully. Systems degrade, ground control compensates, redundancies activate. If all else fails, the crew comes home. At Mars distance, failure is harsher but survivable with sufficient preparation. At Kuiper Belt distances, robotic missions strain but function. Beyond that, in the vast dark volume where the Oort Cloud drifts in silence, the infrastructure of survival itself becomes the thing that fails. Not any single component, the entire framework. The assumption that a mission can call for help. The assumption that a broken part can be replaced. The assumption that a human being can endure the journey and remain functional at the other end. The assumption that the civilization that launched the mission will still be listening when the data arrives. These assumptions hold at the scale of current spaceflight. At the scale of the Oort cloud, they disintegrate. Not because the cloud is hostile. It is not. It is one of the most passive, empty, inert environments imaginable. There is nothing there to attack a spacecraft, nothing to corrode it, nothing to interfere with its systems. The danger is not what the Oort cloud does to a mission. The danger is what it takes away. Proximity to home, access to support, the ability to communicate, to repair, to adapt, to survive a mistake. The Oort cloud does not destroy missions, it isolates them, and isolation, at sufficient scale and duration, accomplishes the same thing. What that isolation means, not just for a single mission, but for the entire trajectory of human expansion outward from Earth, is the final question. And it is the one that changes everything. There is a habit of thought that runs through almost every conversation about the human future in space. It goes something like this: we will master low Earth orbit. We will return to the Moon. We will go to Mars. We will reach the outer planets. And then, someday, we will go to the stars. The trajectory is treated as a staircase. Each step is harder than the last, but the direction is always upward, always outward. And the only question is how long each step takes. The assumption underneath is that the challenge scales smoothly, that the difference between reaching Mars and reaching Jupiter is the same kind of difference as between reaching the Moon and reaching Mars. More distance, more time, more engineering, but fundamentally the same category of problem, harder versions of the same exam. This assumption is wrong, and the Oort cloud is where it breaks. The distinction matters because it is not a distinction of degree, it is a distinction of kind. Going from the Moon to Mars is harder. Going from Mars to Jupiter is much harder. Going from the Kuiper Belt to the Oort cloud is not harder in the same sense. It is different. The nature of the challenge changes. The relationship between the mission and its origin changes. The meaning of the words rescue, communication, support, and return changes. What was once a stretched but functional connection to Earth becomes a theoretical abstraction, a line on a chart that represents a signal too faint to detect traveling a distance too vast to cross in any time frame that matters to the human beings involved. This is what makes the Oort cloud function as a wall, even though it contains nothing solid, nothing hostile, nothing that blocks or damages or resists. The wall is not made of matter, it is made of consequence. And the consequences are not dramatic. They are cumulative, quiet, and structural. They do not announce themselves with a collision or an explosion. They announce themselves with arithmetic, with the steady, relentless multiplication of every difficulty by every other difficulty until the product exceeds the capacity of any realistic mission architecture to absorb. Let us be precise about what this means. A wall, in the most basic structural sense, is something that prevents passage. A physical wall does this by being solid. You cannot walk through it. But there are other kinds of barriers that prevent passage just as effectively without being solid at all. A desert prevents passage not by blocking you, but by removing water. An ocean prevents passage not by resisting your movement, but by offering no ground to stand on, no food to gather, no shelter to build. The barrier is not the presence of something harmful. It is the absence of everything necessary. The result is the same. You do not cross. The Oort cloud operates as this second kind of barrier. It does not block. It does not resist. It removes. It removes proximity to home. It removes the ability to communicate in real time. It removes the possibility of resupply. It removes the option of rescue. It removes the relevance of ground-based mission control. It removes the power margin that keeps instruments alive. It removes the structural integrity that keeps a spacecraft functional across decades. It removes the psychological stability that keeps a human crew coherent across years of isolation. And it removes all of these things simultaneously, across a volume of space so enormous that restoring any one of them from Earth is not merely difficult. It is physically impossible within any time frame that a human mission could survive. This is what separates the Oort Cloud from every other challenge in space exploration. Mars is a problem of engineering and logistics. The outer planets are a problem of propulsion and power. The Kuiper Belt is a problem of distance and communication. The Oort Cloud is a problem of everything at once. Every deficit that exists in deep space mission architecture converges at the same threshold. The tolerances that keep a spacecraft alive shrink to nothing against the same implacable scaling factor. Every lifeline that connects a mission to its origin stretches to the same breaking point and snaps. The word for this in engineering is common mode failure, a situation where multiple independent systems fail simultaneously because they all depend on the same underlying variable. In this case, the variable is distance. And at the scale of the Oort Cloud, distance is not a parameter you can engineer around. It is a condition you must endure. And enduring it requires solving every problem it creates, all at once, with no external help for a duration longer than any machine or any human institution has ever continuously operated. This realization forces a confrontation with something most discussions of human space exploration avoid. The implicit promise of the staircase model, the idea that each step leads naturally to the next, contains a hidden assumption. It assumes that the staircase continues, that there is always a next step, that the engineering challenges, however severe, are always finite. That with enough time, enough money, enough ingenuity, humanity will find a way. The Oort Cloud asks whether that assumption holds, not as a rhetorical question, as a structural one. Consider what would be required to send a crewed mission to even the inner edge of the Oort Cloud at 2,000 astronomical units. You would need a propulsion system capable of reaching speeds far beyond anything currently available, fast enough to arrive within a single human lifetime. No such system exists. The most advanced concepts under study, including solar sails and nuclear electric propulsion, fall short by factors of 10 or more. You would need a power source capable of operating continuously for decades, at minimum, without maintenance, without fuel resupply, without degradation below the threshold needed to run life support. No such power source exists. There is another dimension to the endurance problem that goes beyond power generation. It is the physical survival of the spacecraft itself. Every material degrades over time. Metals fatigue. Polymers become brittle. Lubricants evaporate or solidify. Seals lose elasticity. Electronic components accumulate radiation damage and thermal stress fractures. Solder joints crack. Insulation breaks down. These processes are slow under benign conditions, but they are relentless. And in the environment of interstellar space, near the Oort Cloud, the conditions are not benign. They are among the most extreme sustained environments any engineered object has ever been asked to endure. At the temperatures that prevail in this region, just a few degrees above absolute zero, materials behave in ways that have no parallel in any terrestrial or near-Earth engineering environment. Metals become more brittle. Certain alloys that are flexible and resilient at room temperature become prone to catastrophic fracture under stress. Thermal cycling, the repeated expansion and contraction caused by changes in heat distribution within the spacecraft as systems power on and off, generates microscopic cracks that grow over time. In a mission lasting decades, these cracks propagate. In a mission lasting centuries, they can compromise structural integrity entirely. The Voyager spacecraft provide the only real-world data on long-duration deep space material performance, and the data is instructive. After nearly 50 years in space, both Voyagers have experienced progressive degradation of multiple systems. Thruster fuel lines have clogged as hydrazine propellant residues solidified in the cold. Heaters have been turned off to conserve power, allowing temperatures in certain spacecraft compartments to drop below the design range of the components inside. In 2024, Voyager 1's fault protection system was triggered by a heater-related event, temporarily knocking the spacecraft off its primary communications transmitter. The engineering team recovered the situation, but the incident illustrated a fundamental truth: old spacecraft break. Systems designed for 5-year missions do not function identically after 49 years. And the Voyagers are only at 170 astronomical units. The Oort Cloud is thousands of times farther. A mission to the Oort Cloud would need structural materials capable of maintaining integrity for centuries at near absolute zero temperatures under continuous galactic cosmic ray bombardment. No such material has been developed or tested at that duration. The longest-running materials science experiments on Earth span decades, not centuries. We do not have empirical data on how any engineered material behaves after 300 years of exposure to the conditions of interstellar space. We have models, we have extrapolations, but we do not have data. And building a spacecraft whose survival depends on extrapolations spanning centuries beyond any tested regime is not engineering. It is hope with equations attached. You would need a communication system capable of sending and receiving data across thousands of astronomical units with enough bandwidth to support mission operations. No such system exists. You would need a spacecraft large and complex enough to sustain a human crew in total isolation for the entire duration of the mission, providing food, water, air, medical care, and psychological stability without any possibility of support from Earth. No such spacecraft has ever been designed, let alone built. And you would need a social and institutional structure capable of committing to a mission whose duration exceeds the lifespan of every person who authorizes it, funds it, and builds it. No human institution has ever demonstrated that capability. The institutional problem deserves more than a passing mention because it is, in many ways, the least discussed and most intractable of all the challenges. Every space mission in history has been managed by an institution: NASA, ESA, Roscosmos, CNSA. These organizations design the mission, build the spacecraft, train the operators, launch the vehicle, and maintain communication and control throughout the mission lifetime. The longest continuously managed space mission in history is Voyager, approaching 50 years. It has required constant institutional support across that entire span. Teams of engineers have retired and been replaced. Funding has been renewed year after year through changing political administrations. Antenna time on the Deep Space Network has been allocated and protected against competing demands. Knowledge about the spacecraft's systems has been transferred from one generation of engineers to the next, including, as of 2026, consultation with retired NASA engineers in their 80s who remember details about subsystems designed in the early 1970s. This institutional continuity is fragile. It depends on political will, funding stability, organizational memory, and the physical survival of documentation and expertise. Over 50 years, these factors have been maintained for Voyager, but not without difficulty. There have been periods when the mission was nearly defunded. There have been moments when critical knowledge about the spacecraft's systems existed in the memory of a single aging engineer. The mission has survived through a combination of scientific importance, public affection, and institutional stubbornness. It was not designed to last this long, and the infrastructure supporting it was not built for permanence. Now, extend this problem to a mission lasting 300 years. The institution that launches the spacecraft must continue to support it across a span of time longer than the United States has existed as a country. Longer than the British Empire lasted. Longer than most languages remain mutually intelligible with their earlier forms. The engineers who build the spacecraft will be dead within decades of launch. Their successors will be dead within decades after that. The programming languages used to write the mission software will be obsolete. The data formats will be unreadable without deliberate preservation. The radio frequencies used for communication may be reassigned. The political entities that funded the mission may no longer exist. This is not speculation about unlikely catastrophes. It is the observed baseline rate of institutional change in human civilization. No government, no organization, no cultural structure has ever maintained continuous operational focus on a single technical project for 300 years. The Catholic Church is often cited as an example of institutional longevity, but the Church does not operate spacecraft. Its continuity is cultural and theological, not technical. The operational demands of a multi-century space mission, maintaining trained staff, functioning ground equipment, allocated communication bandwidth, and institutional knowledge about a specific spacecraft's quirks and vulnerabilities have never been attempted or even approximated in human experience. Some researchers have proposed that artificial intelligence could eventually fill this gap, providing autonomous mission management that does not depend on human institutional continuity. If the spacecraft itself were intelligent enough to manage its own operations, diagnose its own faults, and make its own scientific decisions, the dependence on a ground team would be reduced or eliminated. This is a plausible long-term solution, but it introduces its own risks. An artificial intelligence managing a spacecraft in the Oort Cloud would need to be robust enough to function without updates, patches, or corrections for centuries. Software systems on Earth rarely operate for more than a few decades without significant modification. The idea that a software system launched in 1 century could function correctly and autonomously in a radically different mission environment 3 centuries later, without any human oversight, is an assumption that no one in the field of computer science would endorse with confidence. The institutional problem is, at its root, a problem of time, not the time of physics, which is indifferent and precise. The time of civilizations, which is messy, unpredictable, and marked by forgetting. A mission to the Oort Cloud must survive not only the physical journey, but the historical journey. It must outlast the institutions that created it. And it must do so while depending on those institutions for the first several decades of its operational life, before its distance makes independence mandatory. No one has solved this problem. No one has proposed a credible solution, and no amount of propulsion technology or power system innovation addresses it, because it is not an engineering problem. It is a civilizational problem. And civilization, as the historical record demonstrates with uncomfortable clarity, is not a reliable long-term partner. Each of these requirements, taken individually, represents a challenge at the very edge of human technological capacity. Taken together, they represent something qualitatively different. They represent a mission profile that is not merely beyond current capability, but beyond any credible extrapolation of current capability into the foreseeable future. Not because any one component is physically impossible, but because the simultaneous satisfaction of all components at the necessary scale has no precedent, no roadmap, and no funding pathway. And this is only the inner edge. 2,000 astronomical units. The Oort Cloud extends to 100,000 astronomical units or more. The full crossing, from inner boundary to outer boundary, is a span so large that the inner solar system disappears into irrelevance. The distance from the Sun to Neptune, the full breadth of the planetary system, is roughly 30 astronomical units. The distance from the inner edge of the Oort Cloud to the outer edge is roughly 98,000 astronomical units. The cloud is more than 3,000 times wider than the entire planetary solar system. It is not a boundary at the edge of the neighborhood. It is a chasm so wide that the neighborhood itself is a speck at one end of it. Now consider what this means for the commonly held idea that the first great barrier to human expansion is the distance between stars. Alpha Centauri, the nearest star system to the Sun, is approximately 4.37 light-years away. In astronomical units, that is roughly 276,000. The outer edge of the Oort cloud extends to roughly 100,000 to 200,000 astronomical units. This means the Oort cloud occupies a substantial fraction of the distance to the nearest star. At its greatest extent, the outer boundary may reach more than half the way to Alpha Centauri. A spacecraft that somehow crossed the entire Oort cloud would have already completed a large portion of the journey to the nearest star system. And we cannot cross the Oort cloud. Not today. Not with any technology under development. Not with any technology seriously proposed. The journey is too long. The distances are too great. The communication gap is too wide. The power demands are too high. The human factors are too severe. Every analysis that has been done on this problem, from NASA mission concept studies to independent academic assessments, arrives at the same conclusion. Reaching the Oort cloud with a functioning spacecraft, robotic or crewed, requires advances across multiple domains of technology simultaneously, each advance representing decades or centuries of development, and the combination of all of them representing a capability that no serious engineering study has been able to describe in concrete terms. This does not mean it is physically impossible. Nothing in the laws of physics prohibits a spacecraft from traveling to the Oort cloud. The speed of light is not a barrier for a destination still inside the solar system. The energy requirements, while enormous, are finite. There is no exotic physics needed, no warp drives, no wormholes, no violations of known law. The problem is entirely practical. It is a problem of engineering, endurance, and civilizational commitment on a scale that dwarfs anything humanity has ever attempted. And that is exactly why it functions as a wall, not a wall of physics, a wall of practice, a wall of scale. A wall built from the accumulated weight of every limitation that is manageable at shorter distances and crushing at this one. Think carefully about what this implies for the dream of interstellar travel. The stars have always occupied a special place in the human imagination. They are the next frontier, the ultimate destination, the place where science fiction lives and where the future of the species is supposed to unfold. Every generation since the invention of the telescope has looked up and imagined what it would be like to go there. Every generation since the first rocket launches has treated interstellar travel as the natural endpoint of human technological progress. But between here and the stars, there is the Oort cloud, not as a waypoint, not as a rest stop, as a barrier that embodies, in concentrated form, every challenge that interstellar travel would involve. Except worse, because the Oort cloud is still inside our own system. It is still technically home. And if we cannot cross our own backyard, the question of whether we can cross the street becomes considerably less theoretical and considerably more uncomfortable. This is the thought that most space exploration narratives avoid. The popular story jumps from Mars to the stars as if the space between them is merely a montage, a cinematic dissolve from one ambitious scene to the next. The Oort cloud occupies that montage. It is the part of the story no one tells, because telling it honestly would mean admitting that the staircase may not continue, that the next step may not exist, that the gap between what humanity has achieved and what the Oort cloud demands may not be a gap that closes with time and effort. It may be a gap that reveals a permanent structural mismatch between the scale of the cosmos and the scale of the species trying to cross it. Permanent is a strong word. It deserves qualification. Nothing in this analysis proves that humanity will never reach the Oort cloud. Predictions about future technology are inherently unreliable. The history of science is full of confident declarations about what was impossible that were later overturned by discoveries no one anticipated. The people who said heavier than air flight was impossible were wrong. The people who said breaking the sound barrier would destroy an aircraft were wrong. The people who said landing on the moon was a fantasy were wrong. There is a deeper version of this counter-argument that needs to be confronted directly, because it is the one most people instinctively reach for when someone suggests that a barrier might be permanent. The historical analogy, the age of exploration, the great crossings. Humans have faced seemingly impossible boundaries before and crossed every one of them. The Atlantic Ocean was once considered the edge of the navigable world. The Sahara Desert separated civilizations for millennia. The polar ice caps were regarded as lethal, unreachable wastelands. The summit of Everest was thought to be beyond the limits of human physiology. The sound barrier was expected to destroy any aircraft that approached it. The moon was a poetic abstraction, a light in the sky, not a destination. And yet human beings crossed the Atlantic, traversed the Sahara, reached both poles, stood on the summit of Everest, broke the sound barrier, and walked on the moon. Every boundary fell. Every prediction of impossibility was eventually humiliated by someone with enough courage, enough ingenuity, or enough stubbornness to try. This pattern is real. It is one of the most reliable patterns in human history. And it is the reason most people assume the Oort Cloud will fall too. Given enough time, given enough technology, given enough determination, humanity will find a way. We always have. Why should this be different? The answer is that every previous barrier shared a set of structural features that made it crossable, and the Oort Cloud lacks every single one of them. Start with the oceans. When European navigators crossed the Atlantic in the late 15th century, the journey was dangerous, uncertain, and frightening. But it had a set of properties that made it survivable. The crossing took weeks, not centuries. The ships carried enough food and water for a journey of that duration. The sailors breathed the same atmosphere on the open ocean that they breathed on shore. The sun provided light and warmth throughout the voyage. Navigation was possible using visible stars and known currents, and most importantly, there was something on the other side: land, fresh water, timber, food, breathable air, indigenous populations with knowledge of the local environment. The destination was not empty. It was a place where human beings could survive, resupply, and build. The ocean was a barrier between two habitable regions. The crossing was hard. The arrival made the crossing worthwhile. Now consider the polar expeditions. Reaching the North and South Poles required extraordinary endurance, specialized equipment, and tolerance for brutal cold. But the journeys lasted months, not decades. The explorers breathed air. They walked on solid ground or ice. They could, in principle, turn around and go home. Rescue was improbable in the worst cases, but not physically impossible. Ships could be sent. Search parties could be organized. The distance from civilization was measured in hundreds or thousands of miles, not billions. And the environment, while hostile, was composed of familiar elements: cold, wind, ice, snow. Dangerous, but comprehensible. Manageable with sufficient preparation. Even the moon, the most extreme destination humanity has reached, shared these structural features in attenuated form. The crossing took 3 days. Communication with Earth was continuous and nearly instantaneous. The astronauts carried enough consumables for the mission duration with margin. Rescue was unlikely, but not inconceivable. The Apollo 13 crew survived a catastrophic failure and returned home because Earth was close enough for real-time problem-solving, and the transit time was short enough for the crew to endure on emergency supplies. The destination offered no resources, but the mission was designed to be brief. Get there, collect samples, come home. The entire architecture depended on proximity to Earth and the ability to return within days. Every one of these crossings, from the Atlantic to the Moon, shared the same underlying structure. The barrier was finite, and could be crossed within a time frame compatible with human survival using available technology. The environment during crossing, while hostile, did not require the travelers to be entirely self-sustaining. Communication with the origin point was possible within a useful time frame. Rescue or abort, while difficult, was not physically excluded, and in most cases the destination offered something, resources, land, knowledge, strategic advantage, that justified the cost and risk of the crossing. The Oort Cloud fails every one of these criteria, not marginally, categorically. The crossing cannot be completed within a time frame compatible with human survival using any available or near-term technology. At the fastest speeds seriously proposed for deep space missions, reaching even the inner boundary takes centuries. The environment during crossing is the unshielded interstellar medium, requiring the travelers to generate and maintain every condition of their own survival indefinitely without external input of any kind. Communication with Earth degrades from delayed to impractical to functionally non-existent. Rescue is not merely difficult, it is excluded by the laws of physics. No abort, no resupply, no emergency return is possible within any time frame shorter than the original mission duration, and the destination offers nothing: no atmosphere, no liquid water, no surface to land on, no resources to extract, no energy source to tap. The Oort Cloud is not a barrier between two habitable regions. It is a barrier between a habitable region and a void. There is nothing on the other side except more void, stretching outward until tens of thousands of astronomical units later you reach the gravitational territory of another star. A star that, in most cases, has no confirmed habitable planet waiting for your arrival. The historical analogy breaks down because it was never really an analogy at all. It was a category error. The Atlantic, the poles, the moon, these were barriers within the human operational envelope. They were hard. They required innovation. Some of them required courage, bordering on recklessness. But they were crossable because the crossing itself remained within the range of conditions that human beings and human technology could endure. The duration was survivable. The environment was manageable. The connection to home was maintainable. The destination was reachable and, in most cases, rewarding. The Oort Cloud sits outside that envelope, not just beyond its current limits, which could theoretically be extended, but beyond the structural assumptions that made every previous crossing possible. The assumption that a journey has a finite, survivable duration. The assumption that communication with home remains functional. The assumption that rescue is not physically excluded. The assumption that the destination offers something worth reaching. Every one of these assumptions, which held for every crossing in human history from the first ocean voyage to the last Apollo mission, fails at the scale of the Oort Cloud. This does not mean the analogy is useless. It means it has a boundary of applicability. Within that boundary, the lesson of history is powerful and correct. Humans are extraordinary at crossing barriers that sit within the operational envelope. We extend the envelope constantly. We push limits. We surprise ourselves. That record is real and should not be dismissed. But every envelope has an outer edge. And the question the Oort Cloud forces us to ask is whether the outer edge of the human operational envelope falls somewhere inside the solar system, long before the stars, in a region of cold, dark, silent emptiness that offers no foothold, no reward, and no return. History cannot answer that question. History only records the barriers we crossed. It does not record the ones we never reached. But there is a difference between those examples and this one that needs to be stated plainly. Heavier than air flight required mastering aerodynamics and building a sufficiently powerful engine. Breaking the sound barrier required understanding compressible flow and building a sufficiently strong airframe. Landing on the moon required developing rocketry, life support, and navigation systems over a period of about 2 decades. Each of these challenges was singular. It had a primary obstacle. It had a definable threshold. Once the key technology was developed, the barrier fell. The Oort Cloud does not have a primary obstacle. It has a dozen: propulsion, power, communication, radiation shielding, life support, structural endurance, thermal management, autonomous navigation, institutional continuity, human psychology, social stability, resource sustainability. None of these is trivial. All of them must be solved simultaneously, and solving any one of them does not reduce the difficulty of the others. Developing a revolutionary propulsion system that reaches 20 astronomical units per year does not fix the communication problem. Solving the communication problem does not extend the lifespan of a fission reactor. Extending the reactor lifespan does not address the psychological collapse of a crew isolated for decades. Each problem is independent, each is severe, and the mission requires all of them to be solved to the same standard at the same time. This is not the profile of a barrier that falls to a single breakthrough. It is the profile of a barrier that falls only to a civilization operating at a level of coordinated, sustained, multi-domain technological mastery that no human civilization has ever demonstrated. Perhaps one will. Perhaps in centuries or millennia, the species will develop capabilities so far beyond current imagination that the Oort Cloud becomes as manageable as a transatlantic flight. That possibility cannot be ruled out, but it also cannot be assumed, and the assumption is what this story is really about. The quiet, unexamined assumption that humanity is destined to expand outward, that the stars are our future, that the only limit is time. The Oort Cloud challenges that assumption not with a dramatic revelation, but with a patient, detailed, exhaustive accounting of what outward expansion actually requires at the scale where the solar system meets the void. And what the accounting shows is that the solar system itself may already contain the boundary where human expansion ceases to be realistic, not at the edge of the galaxy, not at the threshold of interstellar space as popularly imagined, but here, in the cold, dark region between the Kuiper Belt and the stars, where the sun's gravity still holds, but its warmth, its light, and its relevance to human survival have long since faded to nothing. The most unsettling part of this realization is not the scale of the Oort Cloud. It is the location. This is not a barrier that sits at the doorstep of another civilization, another star, another unknown. This is a barrier that sits inside our own home. The solar system is the sun's territory. The Oort Cloud is part of it, and we may never cross it. The first wall that humanity cannot climb may not be the wall between our star and another. It may be the wall between the inner rooms of our own house and the farthest dark corner of our own property. We may hit the limit before we ever reach the fence. That thought carries a weight that no amount of optimism can fully lift. It does not mean the effort is wasted. Understanding the solar system, pushing outward as far as engineering allows, studying the Kuiper Belt, reaching deeper into the heliosphere, building the technologies that might someday make longer journeys possible, all of this is valuable, regardless of whether the Oort Cloud is ever crossed. The journey matters, even if the destination remains beyond reach. But the honesty matters too. And the honest assessment, based on everything currently known about propulsion, power, communication, human physiology, mission architecture, and the physical structure of the solar system, is that the Oort Cloud represents a practical boundary of a kind humanity has never faced before. Not a puzzle to be solved, not a challenge to be overcome with grit and funding. A structural feature of the cosmos that may permanently exceed the operational capacity of a biological species evolved on a small, warm world orbiting an ordinary star. The sun built the Oort Cloud. It threw icy bodies outward during its chaotic youth. It holds them still with the weakest threads of its gravity, stretched to the breaking point across distances that light itself needs months or years to cross. And the Sun placed this structure between its children and the rest of the universe, not as a wall, not intentionally, not with purpose, but the effect is the same. We live inside a sphere of ice and darkness that may be too large, too cold, too empty, and too far from everything we know for us to ever cross it. The first great barrier is not between the stars. It is here, still inside the neighborhood, still technically home. And the silence out there is the same silence that has always surrounded us. The silence of distance so vast that even light, the fastest thing in the universe, takes years to crawl across it. The silence of a solar system so much larger than the picture in our heads that learning its true size feels less like education and more like a reckoning. The planets are a bright island. The Oort Cloud is the ocean around it, and the ocean may be wider than anything we will ever learn to sail. Not because we are foolish, not because we lack courage or curiosity or the will to try, but because the universe is built on a scale that was never meant for us. It was not meant for anyone. It was not meant at all. It simply is what it is. And what it is, at the boundary of our own solar system, may already be more than we can cross. The stars will wait. They have been waiting for 13 billion years. They are patient beyond comprehension. And they may wait forever, shining in the dark, beautiful and unreachable, separated from us not by the void between them and our sun, but by the cold, quiet, invisible wilderness that our own sun built around itself at the moment of its birth. The first wall is not out there. It is here. It has always been here, and we are only now beginning to understand what it means.